Hello, hey, welcome back. Let's go ahead and take a look at the theorem of what happens when you end up having two chords, are two segments who are fully contained inside of a circle where they intersect. Um, so let's just see kind of how that plays out. And I know theorems can sound kind of scary, and sometimes we're trying to be really, really formal about it. I'm not going to be very formal in this. I'm just going to kind of lay out the logic behind it. And it is really a theorem. It has been proven, and we proved it in class, or maybe for some of you guys will prove it in class if you watch this a little bit earlier. But, we'll see. Hopefully it'll be pretty easy. So what I've got is I've got these two chords right here that intersect inside the circle. Now, this is the way I personally like to lay this out. So imagine, if you will, that I'm in a situation where I have all these pieces. Let's say I have A, B, C, D, and maybe E right here. Now, again, what I wanted to do is develop what happens when we find out some information about the lengths of those chords, specifically what we're talking about today. Now, what I'm going to do is I'm going to make these dotted because I want to be very, very clear that these two lines that I'm going to put in are helpful to get started, but they're not ultimately necessary when we start working. So what I'm going to do is I'm going to make a dotted line from A to D, and I'm going to make a dotted line from B to C. Now, I wrote the word theorem over here because I want to be very, very clear that I am doing a proof. I am showing you where this comes from, but I'm not going to do the two columns. I'm just going to talk our way through it. So the first thing that I notice is right here, these two angles right here are actually going to be congruent because they're vertical angles. So that one part is pretty simple little idea. Now, clearly these are not congruent triangles. You can kind of see one of them is larger than the other. And since they're variables, they could move around. So there's no way these are congruent triangles. But we're going to figure something else out. So again, not being formal, but if you look at angle B right here, angle B intercepts this arc DC. So we would know that this angle right here, that the measure of angle B is 1/2 the measure of arc DC. Because remember, we said that the intercepted arc is half of its, intercepted angle is half of its arc. But something that's also interested is you'll notice that the measure of angle A, see, A also intercepts that exact same arc. So what's kind of important about that is that would tell you if they are both half of that same arc, then they have to both be the same as each other, because I could just substitute. Again, I don't want to be super formal about this, but quite clearly A and B are half of the same value, so they have to be the same as each other. So I can come in here and say these two angles are the same as each other. Now, with that being stated, that means these triangles are not necessarily congruent. I guess they could be, but not generally. But they are similar because they have AA. So I'm going to make my formal little statement that triangle A to E to D is similar to triangle. Now, A is single tick, double tick, single tick, blank. So double single blank, double single blank. That would be BEC. Now, we've seen this in previous stories, but it usually, when we have those intersecting, they're kind of flipped off. But as it turns out, if you kind of follow it, I want to be a little bit cautious about what letters I use. Let me call this one M, this one N, this one X, and this one Y, those length segments. I sometimes like to use A, B, C, D, but I have already kind of used those, and I don't want to be confusing about that. So what I could say, though, is that AE, which is M over here, corresponds to, let's see, AE in one of the triangles corresponds to BE in the other triangle, which is N. And I could say DE, which is X, DE corresponds to CE, which is Y. And as such, what that allows us to do is if you cross multiply, which is always a very, very simple thing to do, that the product of m and y is the same as the product of n and x. So let me see if I could sort of use some colors on that. But notice that I'm saying the product of m and y, and I'm using the same colors kind of on purpose because you'll notice that m and y are really the two portions that make up the chord AC, is equal to n times x. And so notice n times x are right here. So in other words, what we say is two chords intersect, and this is the way we actually say this, is that two chords intersect as a common. Now the word common means identical, like we share that thing, and it's the word product, which is the answer to a multiplication question, because that's what we're doing right here. We're multiplying those stories. So that's kind of the logic behind that, is the product of m and y is n times x. And again, notice that we don't really need a and d anymore, or b and c anymore. We just needed those little segments to establish that these triangles were similar. So here we go. Let's see what happens. So a couple quick examples. First example, real easy one. And that would be this. The product of 3 and 8 would be the same as 5 and x. So 24 equals 5x. Divide both sides by 5, and I got 24/5, which, of course, if you wanted to, 5 goes into 24. I believe that's 4.8 times. I personally like 24/5. Sometimes you get ugly answers like this. Sometimes you get pretty answers. Over here, I could say that the product of 10 and 1 is the same as 2 and y. Well, this time, you get that really nice, easy product where you could see that 2 times 5 and 10 times 1 are the same. Those are so fast. I mean, that's why I'm not sure a lot of you are going to need this video, but this is the part why I wanted to post it. Is that sometimes somebody gives you something that's a little bit awkward, and people obviously just look at this and they're like, I don't even know what to do with it. So what I've got is, let's imagine I did this. Let's imagine I called this x and I called this y. So I know that the product of 3 and 8 is the product of x and y. That's something I know. But separately, see, I've got a little bit of a problem here because I've got two variables and I really only want one variable. But I also know that x plus y, according to this, has to be 10. Or equivalently, I could say y is 10 take away x, because if I subtracted x from both sides. Now, as such, what we can do is I could replace this y here with 10 minus x. And now what you're going to have is this nice little quadratic, which is a nice little reminder we have not been studying it. This doesn't look like a parabola. That's a quadratic. But the mathematics requires us to solve this quadratic formula. So remember, we always like things to be set equal to 0. So I'm going to add x squared to both sides. We don't want this 10x here either. So I'm going to subtract 10x from both sides. And just to finish this up, I've got two numbers that I'm looking for whose product is 24. No shock there, because we saw that, right? But whose sum is negative 10. Now that seems kind of funny because it says the sum is positive 10, but that's just sort of how the math works. And so I could see that both of those answers would need to be a negative 6 and a negative 4. So this has allowed me to factor this story. So I've got x minus 6 and x minus 4. So it appears that the two answers that I got are x equals 6 or x equals 4, which is going to make sense. Now I'm going to use like the color red. If x is 6, then 6 plus 4 is 10. And you can see that this product is 24, but so is 4 times 6. But if you tried the other one, which I don't think I have another color that's easy to use, maybe I could use, I'll just highlight the other option. But if we switched it up and I decided instead of x being 6, what if x was 4? Well, if x is 4, then that makes y 6. And you can see 4 times 6, 6 times 4, same thing, easy to find that answer. I hope that was helpful, and I think that's enough for that. I'll see you guys back in class. Bye-bye.